Hello everyone, I'm Dr. Emilia Bertolo and I'm a principal lecturer in chemistry at Canterbury Christchurch University in the section of Natural and Applied Sciences. This is the first of a series of videos dedicated to energy of reactions, or as we like to call it in chemistry, thermodynamics or thermochemistry. When you finish studying this topic, you will be able to differentiate between an exothermic and endothermic reaction, and you will be able to draw energy diagrams for these reactions. We will be looking also at several thermodynamic variables, including enthalpy, and we will be looking at what enthalpy is and how to perform basic calculations using enthalpies. We're going to be looking at the relationship between enthalpy, entropy, and free energy, Gibbs free energy, and how we can use Gibbs free energy to predict the spontaneity of a reaction. As usual, these videos are not aimed at those students doing a chemistry degree, but all of you who are doing chemistry as part of your own degree. If you have any questions, just drop me an email. It's worth starting with a little definition of what energy is. Energy is a quantitative property. It means it can be quantified, it can be measured, and is the ability of transferring to a body, to what we call a physical system, the ability to either perform some work, for example, moving, or transfer heat or light. Thermodynamics tells us that energy cannot be created nor destroyed. It can only be transformed from one kind to another, and that's what we call the first law of thermodynamics, the principle of conservation of energy. And we are all the time transforming one type of energy into another, and we are surrounded by energy being transformed from one type to the other. For example, when we move our muscles, we convert the chemical energy that is stored in the bonds of the ATP, adenine triphosphate, into kinetic energy that allows us to move. When you turn on your kettle, you are converting that electrical energy into heat energy that warms up your water. So there's all the time energy is being transformed from one type to the other all the time. In a chemical reaction, you have a set of substances that react and produce new substances, and there is some exchange of energy with the surroundings. Sometimes energy is lost to the surroundings, and sometimes the surroundings transmit some energy to the reagents so they can react. So the total energy of the reagents is the same. It has to be the same as the total energy of the products plus any energy that has been exchanged with the surroundings because of the law of conservation of energy. In thermodynamics, we never measure absolute values. You cannot measure the total energy of a substance, because if you think of any chemical compound, it would be the chemical energy stored in those bonds, the kinetic energy for the movement of electrons around the nucleus, the interactions between the protons and the nucleus in the nucleus of the atom. So there is a lot of energy. It's impossible to measure all those energies. But what you can measure is the change, the energy change, and we use the Greek letter delta to talk about these energy changes. So we cannot measure the total energy of a substance, of a reaction. What we can measure is what's happened before and after the reaction takes place and detect that energy change. As I mentioned in a previous slide, we cannot measure the total energy of a system, let's say of a chemical compound. But even if we can't measure it, we have a name for it, because what we can measure is the changes in that internal energy before and after a reaction has taken place. And we call that total energy of our system, of a chemical compound, of a chemical reaction, internal energy, and we give it the letter U. And as I mentioned before, we don't measure total energy, we measure the change in total energy. Any chemical change leads to a change in the internal energy of the system. And when you think of this internal energy and how it changes from the reagents to the product, it appears in two distinct forms. It can appear in the form of heat, being absorbed or released, or it appears in the form of work, either work being done for something to happen or work being released after the change has happened. Work for in a chemical constant, in a chemical context, doesn't really have a particular meaning for us chemists. It's more something that the physicists are more interested on, because our chemical reactions don't quite do work. They might absorb heat, they might release heat, but don't particularly do work. Sometimes they do work in the sense that, for example, if you have a reaction that releases gases, then you can have those gases coming out of the reaction and pushing against the atmospheric pressure to leave. So yes, they are performing some work. Or for example, if the gases are in a closed container, but you have a piston, the gases can push that piston and move it. And again, they are doing some work. So yes, chemical reactions can do work in the appropriate conditions. And if, for example, there is a reaction that involves gases, but it's not what they particularly do well. However, they have a very, very strong tendency to, change. The changes in energy are really visible in changes of heat being absorbed or heat being released at the result of a chemical reaction. So although internal energy is a useful measurement of the energy of the energy changes in a chemical reaction, we chemists are more focused on enthalpy. Enthalpy is the energy left after the reaction has done any work that it's going to do. So for example, if there is gases and gases are being released and they push against the atmospheric pressure, that would be the work of the reaction. So enthalpy deals with the other side, the heat part of the exchange of energy. And in many cases, chemical reactions occur at atmospheric pressure. So we are not particularly bothered about work. So we chemists focus specifically on that enthalpy, the heat aspect of a chemical reaction. And again, we don't measure enthalpy as we didn't measure internal energy. What we measure is enthalpy changes before and after the reaction takes place, how that changing enthalpy is being reflected. When you have a reaction where there are no gases, where there are only solids and liquids, the work aspect, the fact of gases pushing against the atmospheric pressure or pushing against a piston or something is very small. There are the change of in volume that would give you this sort of expansion or contraction of a reaction that would result in the reaction doing work. When you have solids and liquids only, no gases, this volume change is very small. So you can more or less assume that the change in internal energy and the change in enthalpy are almost identical. From the point of view of the enthalpy of a reaction, you can have two types of reactions. The ones that release heat to their surroundings, and we call those exothermic reactions, or the ones that need heat from the surroundings for the reaction to happen, and we call that endothermic. If you have a generic reaction, you can imagine there are a set of reagents that react to form products. The changing enthalpy of that reaction will be the sum of all the enthalpies of the products minus the sum of all the enthalpies of the reagents. And we've got here this little formula with the Greek letters that represent that concept. So sometimes you will have reactions in which the enthalpy of the reagents will be large enough it will be larger than the products. So the products are formed and there is some excess energy that releases in the form of heat. You call that exothermic. And in other cases, you will have reactions in which the sum of the enthalpies of the reagents is smaller than the products you're aiming. So just with the enthalpies of the reagents is not enough. You will need to get some heat from the surroundings for the reaction to happen. So the heat is being absorbed, that energy is being absorbed, and we call that an endothermic reaction. I'm going to ask you to stop the video and have a go at doing this exercise. This is the reaction of the hydrolysis of urea. So this is the compound urea, and it can react with water in the presence of the enzyme urease and produces CO2 and ammonia. And I'm going to ask you to calculate the change in enthalpy, delta H, for this reaction, using the formula we had in the previous slide. The fact that the sum of the enthalpies of the changing enthalpy of the reaction will be the sum of the enthalpy of the products minus the sum of the enthalpies of the reagents. Stop the video now, please. So I hope you had a go at trying this exercise. Let's remind ourselves of the formula. We had that the change of enthalpy of the reaction would be the sum of the enthalpies of the products minus the, let's put it here, delta, the sum of the enthalpy of the reagents. So what do we have as a product? They have two products. We have CO2, carbon dioxide, and ammonia, NH3. And we make 2 moles of ammonia. So if I look at the enthalpy of formation of CO2 is minus 393.5, and the enthalpy of formation of ammonia is minus 46.1, but I have to multiply this by 2 because the reaction does not make 1 mole of ammonia, it makes 2 moles of ammonia. And then I've got the enthalpy of the reagents, and I've got 2 reagents and they are 1 mole each, so I don't need to multiply by anything. One is urea itself, minus 333.5 kilojoules per mole, and the other one is the water, the enthalpy of formation of water, minus 285.8 kilojoules per mole of water. So if I make the calculations for all these, and assuming I haven't made any mistake, I end up with plus 133.6 kilojoules per mole, or kilojoules per this reaction as it is written, per mole of ammonia, per mole of urea, or simply plus 133.6 kilojoules for that reaction in that state with this amount of reagents and products.